Problem 2 on practice exam 4 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We have a double radioactive decay. So it starts off at all oxygen 22, pure oxygen 22, rapidly decays into fluorine 22, which is also radioactive, and that goes away. And pretty soon everything's neon 22. So this is what's happening. Starts off at oxygen 22, decays into fluorine 22, then decays into neon 22. We are looking at the population of the intermediate species, fluorine 22. Grows rapidly in the beginning, as there's a lot of oxygen there and it decays, but pretty soon there's not much oxygen there, so the production rate of fluorine 22 drops, and then the decay rate of fluorine 22 kills that species. So, part A, what is the net change in fluorine atoms over the first thousandth of a second? I think we're ready to tackle that one. The slope of this line everywhere is dn dt because n is on the vertical axis and t is on the horizontal axis. So the change in n divided by the change in time at any point is the slope of the line. To get the decay rate at time equals 0, we need the slope at time equals 0. We don't have the equation, so we need a good tangent line. And there it is. There's our tangent line. The run is tough, but the rise is easy. It goes the whole graph. The run, let's put in a vertical line there. Ooh, look at that, 2 seconds. 2 seconds. So slope is 1.4 times 10 to the 22nd atoms, the entire vertical axis, divided by 2 seconds, the run, and we get about 7 times 10 to the 21st atoms per second. That's the slope, that's the rate at 0. Okay, so that's delta n over delta t. And we can use 1,000th of a second for delta t and solve for delta n. So over the first 1,000th of a second, there are 7 times 10 to the 18th fluorine atoms produced. B, what is the net change in fluorine atoms from 3 to 3.001 seconds? So we have to locate that point, 3 seconds on there, and if we draw a vertical line from the axis, we can find it. It's right there. So let's locate it with a dot, and then we need a tangent line. So let's draw a careful, good tangent line at 3 seconds. The rise, it goes from about 8.4 to 1.4, which is 5.6 times 10 to the 21st, and the run is 4 seconds. So that's the decay rate at 3 seconds. This is the decay rate anywhere around 3 seconds. As long as you're close, that's the decay rate. Delta n over delta t is approximately that, as long as you don't wander too far away. If we put in 1,000th of a second for t, which is not too far, we get 1.4 times 10 to the 18th atoms have been produced from 3 to 3.001 seconds. How long does it take the number of F22 nuclei to drop by 1 billion? Now we should make things a little bit clear here. Here, they're also going away. Fluorine 22 is going away all the time. It's decaying away all the time. Here, when it's going up, the production rate from oxygen 22 is higher. It's still being produced by oxygen 22 out here, but the decay rate of the fluorine 22 dominates that, and the population of F22 goes down. So we're way out here at 20 seconds. There's not much oxygen 22 left. How long does it take for the number of F22 to drop by 1 billion? So we'll locate the point in question, 20 seconds. There it is. We want the rate, so we put a good tangent line in there. Looks like the run is 26 seconds, and the rise is about 9 times 10 to the 21st, a little bit less, and it's dropping, right? The slope is negative, so it's minus 8.9 times 10 to the 21st, and we get minus 3.4 times 10 to the 20th atoms per second. That's the decay rate. That's the change in the number at 20 seconds. Delta population of F22 nuclei. So now we are given delta n. We want delta n is 1 billion, and we want to solve for delta t. So we solve for delta n. We substitute negative 1 billion for delta n, solve for delta t, and we get 3 times 10 to the minus 11 seconds. Not long, right? Light goes really fast, but it'll travel less than a centimeter in 3 times 10 to the minus 11th seconds. D, the maximum number of F22 nuclei present is 1.3 times 10 to the 21st, 1.2, 1.4, a little bit bigger than 1.3 right here. It occurs at 4.275 seconds, 1, 2, 3, 4, somewhere right in here. There's the peak. What's the NDT? Right here. Let's locate the peak. There it is. The tangent line is horizontal. The rise is 0. The run is infinite. What's the slope of that line? It's 0. So dn dt goes from increasing to decreasing at that point.